Hi there, this video is about the heating and cooling curves for states of matter. Let's get started. It is a scientific fact that at ordinary pressure, liquid state cannot have temperature higher than its boiling point and lower than its melting point. Similarly, gaseous state cannot attain temperature lower than its boiling point, and solid state cannot acquire temperature higher than its melting point. Why is it so? Let us explain. Before explaining these scientific facts, let us look at the definition of heating curve. Heating curve is actually plot or graph of change in temperature versus time during the change of solid state to vapor state through liquid state when solid is heated. Now let us look at this figure. It's a figure showing that ice is being heated with the help of a heating liquid, and this heating liquid should be having its boiling point higher than the boiling point of water, and it is actually concentrated sulfuric acid. It is concentrated sulfuric acid, boiling point of which is 338 degrees Celsius. This is outer beaker. This thing is the boiling tube. This is thermometer to record the change in temperature with time, and this is ice. Say for example, this is wire gauze, and this is Bunsen burner as a source of heat. Now it is scientific fact that liquid water, it exists at and below 100 degrees Celsius and at and above 0 degrees Celsius. Similarly, steam, which is the gaseous state of water, it exists at and above 100 degrees Celsius. It cannot exist below 100 degrees Celsius. And likewise, ice, which is the solid state of water, it exists at and below 0 degrees Celsius. Now why this happens, let us explore. In the figure, ice is being heated. We started heating ice at this temperature, say for example at minus 10 degrees Celsius. On heating, when thermal energy is provided, we see that with time the temperature of ice, it increases, as it is obvious from this AB curve, and as soon as the temperature reaches 0 degrees Celsius, ice starts melting, and for this period of time there is no temperature increase seen during this experiment. It means that the temperature of ice cannot be acquired higher than 0 degrees Celsius. Likewise, at this point of time, the entire ice gets converted into liquid water, and again now the liquid water, it undergoes increase in its temperature, and as soon as this temperature reaches, which is 100 degrees Celsius, beyond this time interval, up to this time interval, there is no change in temperature of water takes place. Now why this happens? Although the matter is being continuously supplied with the thermal energy, but from B to C and D to E, there is no increase in temperature of the state of matter. Now why it is happening so? Let us see. We know that when a solid is heated, it melts, and similarly on heating a liquid, it vaporizes. The processes are called melting and vaporization respectively. Similarly, a liquid boils at its boiling point. All these three processes, they require thermal energy, hence they are endothermic processes. They are endothermic processes, means during these processes heat energy is absorbed, heat energy is taken in by the state of matter during these processes. Now let us see that why temperature of ice cannot exceed 0 degree Celsius and why the boiling point of water is discrete, that is 100 degrees Celsius, and it cannot be more than this at ordinary pressure, say at 101 kilopascals. This is ordinary pressure, or 1 atmosphere, which is equal to 1 atmosphere. Now let us see what happens actually. When we start heating ice at minus 10 degrees Celsius, the molecules of ice, they absorb thermal energy, and that thermal energy, which is heat, it is used up to increase the kinetic energy of the molecules. Since the kinetic energy is the direct measure of the temperature of matter, therefore absorption of heat, it increases the temperature of ice from minus 10 to 0 degrees Celsius, and we see that from 0 degrees Celsius onwards, when we heat, the temperature of ice does not change until the entire ice turns into liquid state. Now this curve BC indicates that temperature is no more changing, although we are providing ice continuously with the heat energy. We are continuously heating it, but its temperature is not increasing. Actually, we know that at 0 degrees Celsius ice melts, and since melting is an endothermic process, so the heat energy being provided to ice at 0 degrees Celsius, that is consumed in changing its physical state, that is consumed in changing its physical state. So at 0 degrees Celsius heat energy is consumed in breaking the interparticular attractions. Therefore temperature of ice does not increase until it completely melts to liquid water. So this is the reason that solid state of matter, that can be any matter, cannot have temperature higher than its melting point. Now the minimum quantity of heat energy which is required to completely convert a solid into its liquid state at 0 degrees Celsius, that is called as heat of fusion, sometimes also called as latent heat of fusion, and latent heat of fusion of water is plus 6.02 kilojoule per mole. Now let us see what happens from C to D. C to D state is actually the liquid state of water, and when ice has melted completely and we supply it with the thermal energy, the molecules of liquid water at 0 degrees Celsius, they absorb heat energy, their kinetic energies increase, and this causes the increase in their temperature. So the temperature of liquid water now continuously increases until it reaches its boiling point. But at boiling point the temperature of liquid water does not exceed further until it entirely converts into steam. Now let us see what happens here. Now at the boiling point of water or any other substance, the quantity of heat energy being supplied is consumed in converting the liquid state into gaseous state, that is in breaking the intermolecular attractions. So at 100 degrees Celsius, heat energy provided is consumed in breaking the attractions between water molecules so that it vaporizes, and as vaporization is an endothermic process, therefore the supplied heat would not be able to increase the temperature of water until the entire liquid water turns into steam. So this section EF, it indicates steam, a physical state of water, and so on. So once the water turns into steam, the temperature of steam now further will increase if the heat is supplied further. So in this case, the amount of heat supplied is being consumed to break the intermolecular forces of attraction and to convert the liquid state into steam, which is the gaseous state of water. Now the minimum quantity of heat energy which is required to vaporize 1 mole of water at its boiling point is called heat of vaporization or latent heat of vaporization. Heat of vaporization or latent heat of vaporization. So latent heat of vaporization of water, it is plus 40.7 kilojoule per mole. These positive signs, they indicate that both the fusion means melting and vaporization, they both are endothermic processes. Now let us see in this heating curve what these sections indicate. Now the section A to B, it indicates that water is existing as ice, whereas section B to C indicates that ice is melting, but there is no increase in temperature. In this section A to B, temperature of ice is increasing, temperature increases. Now let us see from C to D what happens from C to D. In this section of this heating curve, water exists as a liquid, and on heating its temperature rises, but from D to E, water boils, it vaporizes and turns into steam, and there is no increase in its temperature. There is no increase in its temperature. Whereas the section E to F, it is for steam whose temperature increases if one supplies thermal energy to it, temperature rises. Now let us see what is the cooling curve, another type of curve for the phase change of matter, that is cooling curve. Cooling curve is plot of change in temperature versus time during change of vapor or gaseous state, change of gaseous state to solid through liquid when gaseous state is subjected to cooling. So this plot is called as a cooling curve of the state of matter. Now let us look at this figure. This guy here is a thermometer. This is outer jacket, and this is a freezing tube. This is steam, and this one is a freezing mixture. It is freezing mixture to cool the gaseous state of matter. Now let us see water as an example, or cooling curve for water. Say for example we have steam at a temperature beyond 100 degrees Celsius. Say for example at this temperature which is above the boiling point of water, and we start cooling it, we see that from F to E the temperature of steam will decrease with time, as it is obvious from this curve. For example, at this point of time temperature is this much, and at this point of time temperature is this much. So with the advent of time, the temperature of steam, it goes on decreasing. So from F to E temperature falls or decreases, and the state of matter or water that exists is steam. So it's again according to kinetic particle theory. Decrease in temperature decreases the kinetic energy of molecules of steam, because of which the molecular motion becomes slower, and the attraction between the vapors of water strengthen, as a result of which they get closer, and as soon as the temperature reaches 100 degrees Celsius, the steam starts converting into liquid water. So from E to D condensation starts at E to D, and since condensation is an exothermic process, so whenever condensation occurs, thermal energy is released, means heat is given out. So the given out heat during condensation does not allow the fall in temperature of vapors at 100 degrees Celsius until the entire steam, it turns into liquid. Temperature remains at 100 degrees Celsius, which indicates that phase change is occurring from steam to liquid water. Now here, although the state of matter is being cooled by the freezing mixture, but its temperature does not fall. The reason is that since condensation is exothermic process, so the amount of thermal energy released during condensation, it maintains the temperature at 100 degrees Celsius until the entire steam turns into liquid water. Now let us see further from D to C. This section from D to C, it indicates liquid water, and F to E indicates steam. Now from D to C, with the course of time, we can see that temperature is falling from 100 degrees Celsius to 0 degrees Celsius on cooling. Again, it can be explained with the help of kinetic particle theory. As the temperature is decreased, means the liquid water now is being deprived of its thermal energy, as a result of which the molecular motion becomes less intense and kinetic energy goes on decreasing until the temperature of the liquid water, it reaches 0 degrees Celsius. But on cooling further, temperature of liquid water now does not fall below 0 degrees Celsius until the liquid water entirely turns into ice. So the section D to C, it indicates liquid water, and it also indicates that temperature falls because the thermal energy is being removed from the system by the cold surrounding, which is the freezing mixture. Now let us see what is happening from C to B. From C to B, water freezes to ice. Since this section of cooling curve indicates a phase change, and during this freezing is occurring, and like condensation, freezing is also exothermic process. So when water freezes, the amount of thermal energy is released, and that released thermal energy does not allow the freezing mixture to fall the temperature of water from C to B, and hence its temperature becomes constant at 0 degrees Celsius until the entire liquid water turns into ice. Once the water has completely turned into ice, then further temperature fall is seen, that is from B to A. From B to A, this section indicates ice and also indicates that with the advent of time, temperature fall has been seen. So this was all about the heating and cooling curves for the states of matter. If you liked the video, please do subscribe my channel and hit the bell icon so that upcoming video lecture on chemistry may not be missed. Sharing is requested too. Thanks for watching.